This video is going to discuss crystal field theory in its most basic level. I'm describing this at a level that a general chemistry student would probably need to understand for a test. You'll take entire courses on this called inorganic chemistry when you further in your career. But basically what we want to talk about with crystal field theory is that complexes involving D and F blocks, they have special properties because that central ion is non-spherical. And if you remember back to your electron configurations, when you drew those orbital shapes, there are 5 orientations. We're just going to look at d orbitals. There are 5 orientations that you can have. Now 2 of them have lobes along an axis. So dz squared is right along an axis, and dx squared minus y squared, I tried to draw it, it's right along an axis as well. And we call those the EG orbitals. They are less stable. There's more repulsion in these. Now the other 3 have their lobes in between the x, y, and z axes. dxy, dyz, and dxz. And you can look up pictures of those in your textbook. I'm not going to attempt to draw those. I'm not a very good artist. But they are more stable because there is less repulsion. And so we call these the T2G orbitals, and they are favored in octahedral complexes. And the energy difference between the EG and the T2G orbitals is called crystal field splitting, which we denote as this delta, that's the Greek letter delta, with a sub-zero. So you'll see a lot of these kinds of diagrams. There's zero energy, and energy is increasing, right? So there's the EG and there's the T2G, and the energy difference between them we call the crystal field splitting. Now in terms of how this relates to absorption spectra, the magnitude of that crystal field splitting can be measured experimentally in the absorption spectrum, and you can measure it in any of these regions of the electromagnetic spectrum. So if your ion captures a photon and gets promoted up to an EG, the energy difference required to do that is just the crystal field splitting. So you're just looking at how much energy it takes to get promoted up here, and that is what we call our crystal field splitting. And this is a figure from a textbook. It's actually my textbook from when I took inorganic chem, and you've got different metals here, right, which would explain why you've got different colors for all the different metals, right? So you've got the blue, green, pink, right? You've got all these different crystal field splitting values. And that's the basics of crystal field splitting. That's where we're going to leave it, and I hope this helps you get started.